Good day, everyone. My name is Rebecca Lilly for the International Association for Energy Economics. It gives me great pleasure to welcome you to today's webinar entitled The Value of Flexibility in Long-Term Energy Planning Decisions. We're grateful to Enzo Swama for today's timely discussion. First, a little bit about the International Association for Energy Economics. We are the largest association specializing in the field of energy economics and provide a forum for the exchange of ideas, experience, and issues among professionals interested in the field. The organization produces 2 professional journals, a newsletter, and holds conferences and virtual presentations along with a host of other products and services you can find at our website at www.iaee.org. If you're not already a member of the association, we welcome you to join. A few housekeeping matters in regard to today's webinar before I hand things over to our speaker. First, this webinar is being recorded for those that cannot participate in today's live event. If you have questions for our speaker, please click the Q&A button at the bottom of the Zoom window and type your question. We've allocated time at the end of the webinar to read and answer them. And now I'd like to introduce you to our speaker, Enzo Swama, professor of the School of Engineering and director of the UC Energy Research Center at the Pontificia Universidad Católica de Chile. Enzo, over to you.
Thank you, Rebecca, and thank you for the invitation to this webinar. Today, we are going to talk about the value of the flexibility in the long-term energy planning decisions. The outline for today is a very brief motivation, then talk a little bit about the value of introducing flexibility, the typical methodology that we use to deal with this flexibility and with uncertainty, some examples, and finally a takeaway of this presentation. So most of the time, the work that we are doing in energy is motivated because of the climate change issue, the global warming, the increase in the temperature because of the CO2 emissions that we are seeing in the planet. And all these issues in general put the alert that the political process it's aware of that and demand acting now. We cannot wait more to see the effect of climate change because climate change is happening today, is having some effect today, and it's going to have more effects in the future. So we cannot wait more. We need to really act now, and that has been the main motivation for example, the increase in the investment in renewable energy. This graph here, for example, shows how has been globally in the world increasing the investment in solar photovoltaics, wind power, hydropower, and biopower, geothermal and ocean power in the world, investment in megawatts. And in 2020, for example, solar PV reached the level that reached the fourth largest source of electrical energy in the world. And it's expected that in the future, solar photovoltaics and wind power increase even more and really becomes to be the main sources of energy, at least in the short term, the electrical energy in the world. But not everything is good news. With all this increase in renewable energy, there is a little problem that the places where most renewable sources are is not the place where most people like to live. Actually, is in general reasonable thing that people don't want to live in very windy places or very sunny and desert places. So the places with the best solar resources or the places with the best wind resources in general are places where there's not much demand for power. People tend to live and demand power in places where are not these resources. This implies that to take the power from the sources to the demand point, we need to build a lot of power lines. And these power lines are costly, takes long time, and have limit capacity. So we really need to plan in advance and very well in advance in time, and having this costly infrastructure in order to get ready for all the renewables that we need. But all these lines also affect in some ways the environment. So there is a discussion of we really need all this infrastructure or not, because there are some other possibilities. Instead of having that much transmission power, maybe we could have more storage. We could have a storage in different ways. We could have a storage like batteries. We could have a storage like pump hydro, like in this project, in which you pump water to a place where you have a reservoir and use it when you need it. Or you even could have batteries for electric cars that, if you have enough electric cars, that could store energy for the network when you need it. All this storage is already possible, but it's not that cheap at this moment, like, for example, bringing cheap power through transmission lines. So there is uncertainty about how it's going to evolve the cost of these batteries. There is also other possibilities for storage, but they have even more uncertainty, because we know that, for example, lithium-ion batteries are decreasing in prices. This is a graph from Bloomberg showing how the cost of the batteries are decreasing, and probably from 2026 or 2030 is going to be competitive, it's going to be economical to have battery for store energy. And that's very important, because renewable resources are not only far away from demand, but also they are intermittent. Wind energy and solar energy are intermittent. Wind energy is intermittent because we don't know exactly when it's going to blow the wind, but solar energy, even in places where you have very few cloudy days, you know for sure that it's not going to be the sun at night. So you need energy at night anyway. So one way to get it is, for example, through this storage system, but still is more costly than other sources of providing energy during the night. But in the future, maybe there could be another ways or another way to get this storage. For example, we could store energy through hydrogen, through the electrolysis process, in which we separate the molecule of water in hydrogen and oxygen. If we use renewable energy to do that, then we perfectly could have store energy in the way of hydrogen. But we don't know exactly how the cost of the hydrogen is going to evolve, when it's going to be competitive, and if it's going to be cheaper than the batteries or not for storing energy. So there is a lot of uncertainty in these decisions. And the problem is that we know that we need to act right now for the climate change, but if we take a decision today, that also closes some doors for the future. For example, if we say, okay, the competitive technology for producing hydrogen, green hydrogen today is alkaline cell, and we use the alkaline cell, well, that is not very efficient like the PEM cell, but it's costly. So if we take this technology today, then probably we are going to block the new technology for some years. So our decision today is also involved that we are taking some decision for the future. And it's important that we take into consideration that when we make the analysis. I'm going to put a very, very simple example to understand this idea with this example of the hydrogen. So let's suppose that we want to compare if we invest in a hydrogen plant for producing green hydrogen today, or we wait. So if we invest today, let's say that the cost is $3.5 million, and we have a small or moderate greenhouse emission reduction because we need to operate this hydrogen plant 24/7, and for that we need to plug during the night, for example, in the grid. So we had, let's say, a benefit of $3 million, and we are going to invest in alkaline cells. And that's one possibility. And let's say that there is two possible scenarios in the future. With half possibility, there is a scenario A, which happened that the technology doesn't have many progress. We still have a very high cost of the membranes, still keep the mature technology as the alkaline cells. We still get the small and moderate emission reduction. And basically, with this scenario A in 2030, we lose 8 years of emission reduction. So that's why the benefit is just $1 million, because we wait 8 years and nothing happened in terms of the technology. So this is a scenario in which it would be better to invest before, but we wait to see if there is a better technology. And a scenario B is that there is a huge progress in the technology. We really get a low-cost technology because this proton exchange membrane, PEM, cells become cheaper and becomes more efficient. So we have massive greenhouse gas emission reduction, and we more than recover the 8 years that we wait. So in this case, in this scenario, we get a lot of benefit of $5 million. Let's say we have these two scenarios. So how we compare this? And in general, what you can see is, well, let's say compute the present value of this alternative. So one alternative is say, well, let's invest today, which have a net negative present value because the cost is $3.5 million and the benefit is only $3 million. So we have a negative benefit if we invest today with this very simple example. And if we consider these probabilities, the expected net benefit, if we wait until 2030 to make the investment, well, is that we get a positive 0.4 million present value, because we have half a possibility to have a very good benefit with low cost, but also we have half possibility that the technology doesn't progress that much. So in this case, with these numbers, for example, the idea is to illustrate that maybe it's not the best idea to just invest in the technology that we have available today, because we don't know if what is going to be the future, and maybe we get expected better value if we wait into the future than if we act now. That doesn't mean that we don't need to do anything today. We need to evaluate this alternative, but this is just to show that it may happen that waiting until the new technology is getting in the future may be a good solution. But now, in this point, is exactly when I want to introduce the idea of flexibility, because there is an alternative of this analysis. This analysis is only comparing two alternatives: the alternative of investing today or investing into 2030. But there is another possibility, which is analyze the possibility to invest today, but having the flexibility to change the investment in the future. So that's the idea of investing with flexibility. So let's put an example today that is a hypothetical example. It's not real, but it's just to give you the idea of what's going on here. So let's suppose that we want to invest in an electrolyzer that is even more costly than the other one. Instead of $3.5 million, it costs $4 million, but have the alternative to exchange the membrane. So can the alternative to move from alkaline cells to PEM cells in the future, of course, with an extra investment. But we could make the change, that we make an extra investment, so we make the system more flexible. With that extra investment, then we could exchange this membrane slot. And that, of course, it costs a little more. But then what happened is that we have the two scenarios in the future. If happen in scenario A, then since the technology doesn't change, there's no extra investment because we are not going to change the membrane, the reduction are the same. We didn't lose the 8 years because we make the investment with alkaline cells from the very beginning, so we still have the benefit of $3 million. So in this scenario, which is the pessimistic scenario, we make the investment before, so we didn't lose these 8 years, which is good. And if a scenario B happened, which means that the new technology, PEM cells, is low cost, then we can make the change of the membrane because we make this extra investment at the beginning, so we can achieve this extra lower cost. We have an extra cost to change the membranes, but we achieve the low cost, and we have the massive reduction of emissions, and we have the benefit, which is farther than before, because we have the benefit from the very beginning and then the benefit of this new technology. And if we we compute the net benefit with this flexibility in this example, it happened that it's higher than all the projects before. So the message here is that if we are able to introduce some flexibility in our investment today, even if that flexibility costs more, maybe it's better for looking at the uncertainty that is going to be in the future. So before going to some examples, I'm going to go through some questions that are in the Q&A post. So if you have more questions, you can write it there. One question is that solar PV largest that I mentioned, if I mean in capacity on gigawatt on energy. Well, it's if I come back to the graph just a little bit, this is about capacity. So in 2020, what solar PV reached is to be the 4th largest electricity capacity. So it is in terms of the gigawatts, in terms of the capacity that is installed, becomes larger than wind and becomes the 4th largest source of energy from the capacity point of view. So it's the capacity that I was talking about. And about the hydrogen that I was talking here, they asked about what about the scale? What are the capacities that we expect for 2030 and 2050? Well, that's an issue. We don't know exactly how is the capacity that we can build and how this is the cost is going to decrease. That's exactly part of this idea. But at least in Chile, that that we have a lot of expectation for the hydrogen because we have a lot of wind and solar power. We are having a lot of projects under construction, and we expect to have 5 gigawatts of power of capacity for producing green hydrogen by 2030. If this is this is the goal. So we are not sure that we are going to get, but this is the goal from the government in Chile. So we expect that we are going to have the 5 gigawatts for 2030, and we are working on that goal. But still, we don't know how far can we go from that goal in the future, because we are creating this large-scale project, but we don't have experience yet. We don't have any of those large-scale green hydrogen plants operating right now. The third question is related with what are the chances that proton exchange membranes cells are indeed developed in 2030. I'm not really an expert in the technology, so the answer is I don't know. What people in chemistry tell me is that PEM technologies is available right now, but it's very costly. So the problem is that it's not commercially available right now. So they need to scale up the prototypes in order to really reduce cost. And if that's going to be ready for 2030, I have no idea. So sorry, I don't have the answer. Okay. Okay, let's take a last question before following that and say how to export the hydrogen to meet electrical demand, since you state that renewable sites are mostly far from demand sites. Okay, that's a good question. There's no exact answer for that today, but there's many hypotheses. So one thing is that well, still is not economical now to store energy in the weight of hydrogen, but let's say that maybe until 2030 or 2040, it becomes economical. So if that happens, we could produce, for example, in the very, very south of Chile, a lot of hydrogen, but it's very far from the rest of the world. So how we get that hydrogen to the rest of the world is an issue. First is that hydrogen is not very easy to store and transport because it's very volatile and need a lot of pressure to be transported and to be stored. So it's very costly today. So it's not clear that it's going to be convenient to have, let's say, in the Chilean Patagonia, production hydrogen and send it to the rest of the world and still be economical compared to the level and cost of hydrogen today. We hope that it's become to be cheaper, but it's not obvious. But one possibility that is under study is that, for example, maybe we don't need to store and transport hydrogen. We could store and transport another vector of energy like ammonia and use the hydrogen to produce ammonia, for example, with the Haber-Bosch process or other electrochemical process, and store ammonia, transport ammonia, and use that ammonia to get the hydrogen, or even have fuel cells of ammonia directly. And maybe that in the future is a more economical solution than moving the hydrogen. The exact answer, as I mentioned, I don't have it, but maybe that's one possibility that people is studying right Okay. What I'm going to mention is, in general, what is the methodology that some people like me use to deal with this uncertainty and with this flexibility that I just mentioned. This flexibility has a value, but also have a cost, of course. And in general, we want to have a methodology to value this flexibility. That this adding flexibility, what is the value that have is it, and this if this value is higher than the extra cost. And one way to value it, this flexibility, is using, for example, real option. Real option is basically the right, but not the obligation of doing certain action, like, for example, the option to expand, the option to leave the project, the option to wait, or the option to grow a project. And we could use that methodology to evaluate the flexibility. And within real options, there are several techniques that you can use to evaluate this flexibility. One is binary trees, that when we have discrete choices is a good alternative. Another possibility could be use least square Monte Carlo simulation, or if you have multiple decisions at the same time, or sequence decisions, you could have like compound least square Monte Carlo. So very quickly, I'm going to show some examples that we have implemented this methodology in some ideas. So in general, the idea is that we have some random process that we can simulate it, like Brownian motion process, geometrical Brownian motion process, and we have simulation of this random process to, for example, estimate the supply or the demand or certain parameters of certain model. And we use those trajectories to compute the value of this flexibility or the value of implementing a flexible project. And we compare that flexible project with, in general, with the rigid project, which have no this flexibility, and then we can evaluate this flexibility. Let's show very quickly 3 examples that we implement with this methodology. For example, in Chile, in 2018, there were 2 separate systems, which is the north system and the central system, and we connect both systems with this line. And there was, at that time, a lot of discussion of we should implement a very high capacity line from the very beginning, on if we should put a line with less capacity at the beginning and have the possibility to expand the capacity in the future. So basically, the idea to try to illustrate this is, okay, we have the possibility to have an investment today with certain capacity, or we could have a different kind of tower, which of course is a little more costly, but have the possibility of not only having the current capacity that is planned, but also in the future you could have more cables and more capacity without having extra towers. We use the same infrastructure, you have just a little more extra cost for the cable. And that's the flexibility that we evaluate here. If it's better to have these towers and with the possibility to invest or to expand the capacity of the lines in the future. And of course, the flexible project to evaluate the value has a cost, because you have an extra cost of these towers, because to have this possibility compared to the normal investment. So this is the difference in cost. And if you implement it, you need to have also an extra cost of the cables. But you only implement it if it's needed, if demand increases a lot and you really need the extra capacity. So we could simulate using least square Monte Carlo, a lot of trajectories of how to be the demand in the future, and we can compute the value, the present value of this flexible project. So in this case, for example, the possibility to having the flexibility has a positive value. So it's better for us to have this flexible project instead of just making the decision today with a fixed capacity for the line in the future. So in this case, we can evaluate using this methodology the flexibility of investing today. Another project that we have, another example is that we use almost the same methodology to make the decision in a residential house to see if it's convenient to install solar panels and batteries. So what we use here is to have different possibilities. We don't have anything installed right now, and we have the possibility to install 2 different levels of capacity in solar panels. And then we have also the possibility to invest batteries after we invest in panels, or we can directly invest in solar panels and batteries. We could have any of these state at any moment. So the difference here with the other project is that in this case, we allow investment in multiple steps. So we could invest, for example, first in certain capacity of solar panel, then we could invest in more solar panels and some batteries, and then we could invest in more batteries, and we could move in any of these directions, always increasing the capacity. So there is a different investment paths, and we evaluate this, the flexibility of having all this path and all this possibility in the same way that we have before. So we have some simulation using this from Monte Carlo, using geometric background motion for the electricity price, for the evolution of the cost of the model, the evolution of the cost of the batteries, and then we can evaluate what is the best path to market. For the case of Chile, with the cost that we have of solar panels in Chile and with the cost of batteries in Chile, it happened that for residential people in the metropolitan region in Chile, the most popular path is going first to install the maximum capacity of solar panels and then move to install also some capacity of batteries. And that's happened in the 75% of the cases, and in this from this 31.7 times goes to this state, and in 23 or 4% of the times, so mostly of the rest, go directly to this state. So that also allows us to measure the value of having this flexibility. And the flexibility in this case, that we have these 2 kinds of flexibilities, the single flexibility and the compound flexibility. The single flexibility is when we allow to have 2 periods of investment. So we could decide go, for example, installing solar panels and then installing batteries, but only these 2 steps. And the compound flexibility is that we allow any possible path. So we could have, for example, first going to the minimum capacity of solar, then increase the solar capacity, then move to batteries, and at any time within a horizon that we consider 25 years. And we can see that the value of the flexibility increase, especially in the case that we have more batteries and more solar panels, because when we have this flexibility, we are going to install the maximum capacity of solar panels and batteries only if demand is higher. If not, we are going to stay in a low level. So that flexibility increases a lot of the value of having this flexibility. We are not going to exercise always this from the very beginning, and that flexibility has a lot of value, especially if there is a lot of uncertainty in the future. And the final example that I'm going to show, because I want to have time for questions, is using real options. We determine when and on what capacity of hydrogen production we need to build for a green hydrogen plant. And in general, we consider that we have an investor that will invest in solar panels, in electrolyzers, or directly in both at the same time. We consider that this electrolyzer, of course, when it's available with solar panels, it's going to use the energy from solar panels, but when it's not available, the solar energy is going to be connected to the grid. Again, we use Monte Carlo simulation to see the evolution of the price of hydrogen, the price of electricity, the evolution of the cost of solar panels, the cost of electrolyzers. We still, like in the other case, we have different state of investment that we can move from any state to other with higher capacity. The results show that, again, in the north of Chile, in this case, the most frequent path is to first in the first years, from now to 2030, the most common, almost always, the best decision is to install the maximum capacity of solar panel, but not electrolyzers today, but wait further than 2030 to install electrolyzers in almost 2/3 of the time in the maximum capacity of electrolyzers, but like 1/4 of the time investing in the minimum capacity of electrolyzers and sometimes moving then to the maximum capacity. Okay, and we have always this evaluation of the flexibility. Again, we have in some cases negative value, but in which mean this is the rigid project, which means that if we, for example, install electrolyzers or solar panels and electrolyzers today, and we keep it for the whole horizon, but it's a rigid project, we don't have the flexibility, the net present value today is negative. But even if we install the same electrolyzer, but we have the flexibility to see when we install that, and we have the flexibility to install in steps, then has a positive value. And if we have, for example, the possibility to install solar panels and electrolyzer, but with full flexibility of when we want to install and how many steps we want to use for those investments, the flexibility is even further. So that's the value of the flexibility. We make a lot of sensitivity analysis on that, but I want to close the presentation with this takeaway, which basically say, well, adding flexibility to the energy planning decision process may be valuable. So maybe it may happen that the best decision maybe is not to invest as quickly as possible in an environmental friendly solution, because that can block the possibility that we are going to have in the future. And we know that uncertainty is in the process. So if it's possible to add flexibility, then that maybe is a better solution that invests as quickly as possible in a rigid process today. Some economic tools or real options can help us in the evaluation of this flexibility, and the value of this flexibility in general in all our examples increase as more uncertainty is handled. So process like the hydrogen, the green hydrogen, which has a lot of uncertainty on how it's going to evolve the cost, maybe the flexibility is a lot more valuable than in other processes that have less uncertainty. So I'm going to stop here. I'm going to thank all of you, and I'm going to take some questions. If you can write the questions in the question and answer block. Okay, so Christine have a question about the transmission example. If there is a paper published on that the answer is yes. We have a paper for each one of these three examples. Maybe, well, in the first two examples, they are published. In the third example, it's just submitted. So I'm not able to facilitate the right now. But for the first two examples, the transmission and the residential solar panels and storage, there is some papers that are published. So I think that the best way is that I can send to Rebecca, and then Rebecca can distribute to whoever is interested in the papers. If that's okay with you, Rebecca.
Absolutely fine.
Okay, so another question is about hydrogen. You can talk mostly about hydrogen production. How about demand? Which demand to expect? How do you create this demand market? Well, that's a very good question. Demand for hydrogen, well, is actually happening today, not at those levels that we expect, but there is a demand for hydrogen today. What is going to be the demand in the future, we don't know, but there is a warning with all this war between Russia and Ukraine, and with the global warming issues, that probably we really need to change the fossil fuels consumption, and we really need new fuels. And in that way, if the technology is able to have, for example, trucks, especially in mining companies that have a very heavy trucks, trains, or even airplanes that can use hydrogen fuel cells, or even ammonia fuel cells, then the demand is going to increase exponentially. There is some estimations by Bloomberg or by McKinsey that demand of hydrogen is going to be much higher than the potential for production of hydrogen or ammonia by 2040. But of course, these are only projections. We don't know about how that demand is going to increase. But everything point to the replacement of fossil fuels. And the replacement of fossil fuel today is probably going to happen in the direction of the hydrogen or ammonia. So that is the expectation that the forecast that the demand is going to increase, or can increase considerable in the next 10 years. Okay, so another question is from Mohammed Reza. Is in this study is assumed that I'm assuming that this example too, this is in this study, it's assumed that the PV plant doesn't participate in the electricity market by offering for selling their produced power. By their participation in the electricity market, the behavior of the other players impose further uncertainty in the decision process of the PV plants. Maybe the planning for batteries and other flexibility providers change. Would you please shed some lights on this point? Okay, there's several ideas here. in our example, and that's why it's useful to share the papers, we do consider that the investor can sell the power from the solar panels. So they can sell in the market directly the electricity from solar panels instead of using, for example, in example 3, for using hydrogen or to store in the residential level. The point here, that is a very simplistic assumption that we have in the paper, is that the price of electricity is not endogenous, but this is exogenous because it follows a geometric background motion process in our paper. So we have an electricity price that is exogenous, is a parameter that we simulated. So in real life, probably there is an endogenous process that investment in solar panels is going to influence the price of the electricity, and that we are not reflecting in our paper, which is true, that could be a next step. So the question is that we consider the possibility of selling power to the network, but at a fixed price. So there is still work for doing to see how the endogenous impact of the price of electricity influence this flexibility and influence this investment. Okay, I cannot see more questions, so I don't know if you have a live question or you want to write more questions. Okay, I don't see more questions, so I come back to you, Rebecca.
IAEE wishes to thank Enzo Suoma for an outstanding webinar. This webinar will be available on IAEE's website for future download. Also, if you want to send me the paper you were discussing, I'll be happy to post that as well. If you're not a member of IAEE, we encourage you to join by visiting www.iaee.org. We thank you for attending, and I officially close this webinar.